Hello again. We continue from the point where we ended in lecture number 1. So this is lecture number 2 for Math 609. We were discussing last time Gauss elimination, and we were discussing the case when we start with a matrix A, and let's say we will consider the two cases if we have the system AX is equal to B, and if we start with the matrix A and let us write A is equal to A. And we consider the case that every time we perform Gauss elimination, the entry of the resulting matrix that sits right here, the entry AKK, which we call a pivot element, is different from 0. If every time after we perform a step, the pivot element is different from 0, we can compute the numbers LKJ through this formula. LKJ is equal to AJKK divided by the corresponding pivot element, which, if you would like to visualize, it is the element that sits on this position, the element L that sits on this position is just the ratio of the corresponding blue element and the corresponding red element. So everything that sits on position K plus 1K is the ratio of the current element that sits there divided by the pivot. The element L with index MK is the ratio of the current element that sits on position MK divided by the corresponding pivot element. This is how we create the numbers L, K, LJK. And then using these elements, we create the corresponding lower tridiagonal matrix LK that has ones on the main diagonal and has the corresponding L's on column K below the main diagonal with negative signs. Now, we also discussed that if we start with the equation A is equal to A, then we perform one step of Gauss elimination. The performance of one step of Gauss elimination means that we multiply on the left the matrix A by the corresponding matrix L1. So we have L1A is equal to L1A. Then we perform a second step of the Gauss elimination. We can do that by multiplying on the left the resulting matrix by the matrix L2, where the structure of all the matrices LK is the following. You have 1 on the main diagonal, and below the main diagonal on column K, we have these L's with a negative sign. Then this is equal here to L2, and so on. At the very end, we have a multiplication with the matrix Lm minus 1. And here at the very end, we have the multiplication with the matrix Lm minus 1. So once we have that, as a result, the matrix that we end up with is the upper triangular matrix U, and so we have that Lm minus 1 and so on, L2, L1A is equal to this upper triangular matrix U. And in the previous lecture, we had exactly this equation, and from this equation, we discussed that this equation can be translated in the form A is equal to L times U, where the matrix L is equal to the product of the inverses of these matrices LK. We know that the matrix U is an upper triangular matrix. What we need to show is that the matrix L is a lower triangular matrix, and this is what we are going to do next. Before doing that, let's see how this works if we have to solve a system using Gauss elimination. If we multiply, so we continuously here multiply by L1, both sides of the system, then we multiply the same as we did here, then we multiply by L2 and so on, and at the end we will have Lm minus 1 and so on up to L1 multiplied by Ax will be equal to Lm minus 1 and so on multiplied by L1 times B. So this will be some new vector, which will be C, and this here will be exactly the upper triangular matrix U. So using Gauss elimination, every system Ax is equal to B can be rewritten in the form Ux is equal to C, where U is an upper triangular matrix. So it has this structure. Here is something, and on the main diagonal there is something, and everything below the main diagonal is equal to 0. And then to solve this system, we simply use the backward substitution, because the backward substitution is giving us the solution. And we know that the cost, the operational cost to solve the system using a backward substitution is m squared, where m is the dimension of the problem. Therefore, the cost to solve the whole system, Ax is equal to B using Gauss elimination, is the cost of finding the matrix U plus the cost of the matrix, the cost of solving this linear system. Now, after we discuss the form of the matrix L, we will discuss the cost of finding the matrix U, which is the cost of the Gauss elimination. So let's go further. We said that in our equations from before, we had the form for L. This is the product of the inverses of the matrices Lk. So what we have that the matrix A is the product of the matrix L and the matrix U, provided that all the pivot elements A, K, K, K that arrive during Gauss elimination are different from 0. And we show that the matrix L is actually the product of the inverses of all these matrices Lk. And we know what the form of a matrix Lk is. What our goal now is to find what is the matrix L. In order to do that, we are going to rewrite the matrix Lk in a more friendly form. And in order to do that, we will use the vectors little lk and the column vector ek, which basically is the standard basis vector that contains all zeros, except that on position k, it has a value 1. If we look at the matrix Lk here, we see that it consists of the identity matrix, and it has this part here below the main diagonal on the kth column. So I can rewrite this matrix Lk as the sum of two matrices, actually as a difference of two matrices. So the first matrix will be the identity matrix, which will take care of all the diagonal elements, and then minus because of these minuses right here. And then I will write the matrix that has zeros everywhere, except that here, if this is column K, and if here this is row K, this will be on the main diagonal, it will have 0 on this main diagonal, and below it will have the L's, Lk plus 1k, and so on. It will have Lmk. K. So this is this piece here of the original matrix. I can just decompose the matrix LK as a difference of the identity matrix and of this matrix, where everywhere else I have zeros, but on the kth column below the main diagonal, I have all the LKs. Now, if I do that, what is happening is that this is the identity I here, minus, here is this minus here, and then I would like to represent this matrix in some way. And a convenient way to represent this matrix is to write it as a product of the vector LK and the vector LK. You can think, since we're talking about real entries of the matrix, you can think of this EK transpose. So I is a matrix that is of dimensions m times m. LK is a vector column, which is of dimension m times 1. EK transpose is a vector row, which is of dimension 1 times m. And when I multiply those two vectors, I will end up with a matrix of dimension m times m. So once I multiply LK by EK transpose, I will end up with a matrix that is of dimension m times m. And what will be, so here is 0, 0, and so on, 1, and 0. This is the vector AK transpose. So if you do this multiplication with LK and EK transpose, using the rules of matrix multiplication, you will end up with exactly this matrix here that has zeros everywhere, except that on the kth column, all the elements below the main diagonal are the corresponding L's. And therefore, we have another representation of the matrix LK. Now, the first claim that we are going to prove is that LK is in fact an invertible matrix, which is not so difficult to see because this is a lower triangular matrix with ones on the main diagonal. Therefore, the determinant of this matrix is 1 as product of all the elements on the main diagonal, and therefore it will be invertible. The more interesting part is how to compute the inverse of this matrix, and the lemma tells us that the inverse of this matrix is in fact also a very simple matrix. This is the same basically as the matrix LK. The only difference is that here, instead of these minuses, we have pluses. So just we drop the minuses. This is how we can write the formula for the inverse of this matrix. So this is the lemma. And the proof of the lemma is not so difficult. So to show that LK inverse is this matrix, we have to show that the matrix LK multiplied by this matrix gives us the identity. And the same way as we will show here, we'll come back in a minute to prove that, to show that this matrix here that we claim is the inverse of LK multiplied by LK is the identity. And therefore, the inverse of the matrix LK is I plus the product of LK and EK star, where and therefore the formula for LK inverse is this. We have ones on the main, or the form of LK inverse is this. We have 1 on the main diagonal, and here we have column K, and in this column K, everything below the main diagonal are actually those L's, where again, what is LJK? LJK is AJK K divided by AKK. And again, what were those? Those were all the elements below the pivot element in the kth step. So this divided by this, and so on, this divided by that. To continue our proof, let's look at this product here. And let's write down the formula for our matrix LK, which we saw here that there is another a convenient way to represent the matrix LK. And now do the matrix multiplication. I times I will give us I. Then we have I times LK EK star is this term. Then we have minus LK EK star times I, which will give us this term. And then we have the multiplication of this term with this term. And we have to be careful that matrix multiplication is not commutative. So we have to write exactly the order in which these factors appear. So first LK, then EK star, then LK, and then again EK star. Clearly, those are two matrices with opposite entries, so we cancel them out. And we use the fact that the product of matrices is multiplication of matrices is associative. That means if I have A times B, and then I multiply the result as with the matrix C, that this is the same as multiplying A by the product of B and C. And therefore, in this product here of four vectors, which I view as matrices, I can put the parentheses everywhere I want. And so I decide to put the parentheses right here. And I want to see what this is. EK transpose is vector, which I can view as a matrix of dimension 1 times m. And then LK is a vector of dimension m times 1, right? Remember that LK here was this vector, which is the vector column of dimension m times 1. And therefore, EK times EK transpose times LK, when I do the multiplication, this is a matrix of dimension 1 times 1, or in fact, this is a number. And the question is, what will be this number? So if I have the vector EK transpose, this is 0, 0, and so on, 1, 0, and so on, 0. So here is the K. And I multiply this vector by the vector LK, which is 0, 0, and so on. On position K, I have 0 here. And then after that, I have LK plus 1K. And so on, I have LMK, right? Remember, this was the vector LK. On position K here, it is 0. So this position K here is 0. And after that, from position K plus 1 to M, it fills in with the M's. Well, if I do this multiplication, then the only place where I can have a hope of non-zero term is when the 1 will hit some entry of that vector LK, but the 1 sits on K position. So if I do the multiplication, the 1 will hit exactly this term here, which stays on Kth position, which is 0. So this number is nothing but the number 0. And this number, as a number, I can pull out. And therefore, I will have the number 0 multiplied by some matrix, which will give me the 0th matrix. And therefore, the result is the identity, which gives me that indeed the matrix LK multiplied by this matrix is the identity. In similar way, one can show that this matrix times the LK is equal to the identity, and therefore a simple formula for finding the inverse of the matrix LK is this formula. Now, what do we have? We have that the matrix L, as discussed before, is a product of these inverses. And therefore, the matrix L will be, since we found the inverses of each of the matrices LK, this will be this matrix, which is inverse of L1. Then the inverse of L2 will be this matrix, and so on, that the inverse of Lm minus 1 will be this matrix. And what we need to show what is the structure of the resulting matrix. And the next lemma tells us that the structure of the resulting matrix is this. We have the matrix L is equal to, it is a lower triangular matrix. Everywhere on the main diagonal we have ones. Everywhere above the main diagonal, we have zeros, and below the main diagonal are those exactly numbers that we have. And what are those numbers, LJK? Those numbers are the AJKK divided by a KKK. So after performing the first step of the Gauss elimination, we can fill in the first column of the matrix L below the main diagonal, because after the first step of the Gauss elimination, we will know these ratios, which is at the first step, this is my pivot element, and therefore I will have the ratio of the second element divided by the first element, and so on, the mth element divided by the first element. This is how I will get my L's, and these L's will be put under will fill in the first column of L. Then I do the second step of my Gauss elimination. In the second step of my Gauss elimination, this is the pivot element, and the pivot element occupies the second column. Then I look at the corresponding ratio of this element divided by the pivot element. This is the corresponding L with the same index with the same indices as the indices of the numerator of that ratio. And so on, I will compute all the L's that occupy the second column of my matrix L. So I will compute all these L's, and this is how I'm going to fill in the all the elements below the main diagonal on column 2, and so on. So the lemma, to go back to the lemma says that the formula for L is this, and in fact, this tells us that using Gauss elimination, we for free get the matrix L for free, get the elements of this lower triangular matrix that participates in the LU factorization of the matrix A. So to do the proof, we will first prove this product here. And then we will see, we're not going to go into details further what will happen, but we will just examine the product of the first two matrices. Again, this is the identity, because identity times identity is the identity. Then this, after that, it is L1 E1 star, then it is L2 E2 star, and then this is this matrix L1 E1 star times L2 E2 star. And as we did here, we know that we can put parentheses everywhere in this product, and we decide to put the parentheses right here. If we put the parenthesis here, what is the vector E1? The vector E1 transpose is 1, 0, 0, and so on. And what is the vector L2? The vector L2 is 0 on the first position. And if you look carefully, what was the vector LK? We have at K position 0, so it will be 0 also at position 2. And then after that, we will have the terms L3, 2, and so on, LM2. So if we do this multiplication, we'll see that the only place that one will have a hope to end up with a non-zero term, because these zeros will make everything else 0, will be the multiplication between the 1 and the first term here, which will be 0, and therefore this product here will be 0. The fact that this product is the number 0, that number can go out and will make the whole matrix 0. Therefore, the product of the first two matrices right here is the matrix I plus L1 E1 star plus L2 E2 star. Let me remind you that this means that if we look at the first product, I will have the identity matrix and so on. Then after that, L1 E1 star will populate this first column of the matrix, of the resulting matrix. So I will have here L21 and so on, LM1. Then L2 E2 star will populate the second column. So here I will have L32, and so on will have LM2, and everywhere else will be 0. So this matrix here will be exactly this matrix here. So it will have, once on the main diagonal, will populate the first column and below the main diagonal, and will populate the second column below the main diagonal, and everywhere else will be 0. And then if we continue the same way, doing the product of this matrix and the next matrix I plus L3 E3 star, having similar considerations as before, we will end up that the result is the identity plus L1 E1 star and so on, plus LM minus 1 EM minus 1 star, which will give us that after every product, we will be continuously filling in the first column, then the second column, and so on. At the very end, we will fill the M minus first column below the main diagonal, and we will end up exactly with this form of the matrix L. Now, what is going to be the actual algorithm if we decide to program Gauss elimination? We go back to what we ended up in the previous lecture, namely those rows here that tell you how to compute the numbers LJK, by which you will multiply the kth row and add it to the k plus first and so on up to the mth row. And this is the actually multiply this number with a negative sign and then add it to the k plus first and so on to the mth row. And these two rows are programmed in here in some sort of a semi as an algorithm without any use of any particular language. So what we start with, we set that the matrix that we would like to end up with U, we set it first to be equal to the matrix A, and the matrix L to be equal to the identity, and then we gradually will populate the matrix L. And so we start for k from 1 to m minus 1, and then the index j is from k plus 1 to m. We find the elements L. These elements will be the elements that will populate the lower unit triangular matrix. And then, as we discussed, that the new elements of the matrix U, the new entries of the matrix U from position k plus 1 to m will be equal to the entries that from to the jth. It is right here. It is the same equation. The new element on position ji will be equal to the old element of position ji. The old means with index k minus this index ljk minus the times the corresponding element on the that sits on the kth row and the ith column. And here it is written in a syntaxis in which instead of having the second index running from k plus 1 to m, this tells you that the second index basically changes from k plus 1 to m. So this is the algorithm. In practice, as I discussed before, the matrices LK are never formed and never multiplied explicitly. This is what is done in practice, that algorithm. LJKs are computed, and as we discussed, using this ratio, and they are, this is how they are stored here to find the matrix L. And the transformations LK are applied implicitly. They are applied here. These are the transformations LK, multiplying on the left by the matrix LK, the resulting matrix of the Gauss elimination at step K. And to minimize memory, we can use L and U to be written into the same array as A. So if A originally, for example, was this 3 by 3 matrix, so how can we store? We can store the matrix U as the upper part of the matrix of the storage of the, basically if we think of the memory as this. So the upper part here will store the elements of U, and everything below the main diagonal will store the elements of L. We do not need the elements of L on the main diagonal because we know that they are all ones. So this is in terms of storage. And now to example, we'll do some simple example as to how we perform Gauss elimination. So we start with this matrix, and what we need to do, first of all, if I have to, so let me do it independently of what is written here. So we know that the matrix L is a matrix that will be a 3 by 3 matrix. It will have ones on the main diagonal. Above the main diagonal, it will have zeros, and we have to fill in the element below the main diagonal in the first and in the second column. To fill the elements below the main diagonal in the first column, we look at the first column of A, and we look at the ratio of this element divided by the pivot. So our pivot element here is the top one. This is the pivot element. So we have this element divided by the pivot, and we put it in position 2, 1. So we have minus a half, which is equal to minus 1 divided by 2. So minus 1 divided by 2. And then in this position here, we take this element that stays on the same position in the original matrix A and is divided by the pivot. So we have 0 divided by 2, and it will be on position 3, 1. We end up with 0, and this is 0. So at the first step, we can only compute the first row, the first column of the matrix L. And in fact, we can compute only everything below the main diagonal in the first column. Then we continue with the usual Gauss elimination to make all these elements 0. So what do? We multiply by 1/2 the first row and add it to the second row. And we keep the first row as is. Then we know that when we do that, this element will be 0. Minus 1 times 1/2 plus 2 will give us 2 minus a half, which will give 3/2. And then a half times 0 minus 1 will give us minus 1. This is how we modify the second row. And then we don't need to modify the third row because it already has 0 there, so we just put it down. Repeat it. If we want to use the algorithm, what multiplied by the first row and add it to the third row will make this term 0. Well, it is 0, and therefore we do not change this row. Now from here to go to the next to end up with the upper triangular matrix, before performing the next step of Gauss elimination, we have to fill in the second column of the matrix L. We look to fill the second column of the matrix L. We use only information from the second column of the matrix on the corresponding at the second step of the Gauss elimination. And what we do, we look at this second column and we divide by the pivot element all the elements below the pivot element. So here we have only 1, so we have minus 1 divided by 3/2 will give me 2/3 with a negative sign. So I end up with -2/3. And this is exactly what the matrix L is. I am done now with the matrix L. And to continue with the Gauss elimination, I save the first row as it is. I save the second row as it is because they are having the corresponding zeros. And now I want to modify this. What do I multiply the second row to add to the third in order to make this term 0? So I multiply by 2/3. And when I add, I know that I will end up here with 0. So I have 2 plus -1 times 2/3, which is 2 minus 2/3, which will give me 4/3. So I ended up with finding the matrix U and also finding the matrix L. So in this particular case, we see that all the pivot elements, which here are 2 and 3/2, are different from 0, and therefore all the steps of the Gauss elimination can be performed, and therefore we can write the matrix L as a product of the lower unit triangular matrix L and the upper triangular matrix U. And of course, we can check now that the matrix A is indeed the product of the matrix L and the matrix U. Then the next step is to do the operation count. And let's see what are the number of divisions, subtractions, and multiplications here. As I said in your book and in some books, they count only the number of divisions and multiplications because those are the most computationally extensive operations. In some other books, they count the flops, which are the floating point arithmetic operations, and therefore there is a slight difference in the actual number that you end up with, but we are going to do the flops. And so let's first look at step by step what is happening and see what how many divisions, subtractions, and multiplications we have. So if we look at the first step, what did we do in the first step? In the first step, we basically computed all the L's for the first column. To compute all the L's for the first column, we had to divide this number by the corresponding pivot element, the next number by the corresponding pivot element, and so on, the last number by the corresponding pivot element. So as a total, we have a matrix is of dimension m times m. So we have from second down to m, we have m minus 1 divisions, and these m minus 1 divisions were the divisions for the computation of the L's. So we write down for step 1, we have m minus 1 divisions for step 1. Then we'll look at the subtractions, the number of subtractions and the number of multiplications. Once we do that, let's go back to where we were. Once we do that, then what do? We multiply each term here by the L. So this is one multiplication, and add it to this term here, which is one addition. Then this term here multiplied by L, one multiplication, add it to this term here. So to make, we do not discuss what will happen here on the first position on the second row, because we know that this will be 0. This was the way we selected L, so we do not count those as operations because we know that they will be 0 when we even don't perform them. So we have multiplication of each of the terms here, which are m minus 1. So we have m minus 1 multiplications, and we add this to each of those terms here to compute the corresponding elements of the next of the matrix of the next at the next which is going to the next iteration, which will be with upper index 2. So basically we have m-1 addition, m-1 multiplications and m-1, think of them additions or subtractions, doesn't matter. And this is for this row, but we have m-1 row. So for every row we have m-1, and we have m-1 row, so we'll have m-1 squared additions and m-1 squared multiplications at the first step. Now, when we move to the second step, this basically repeats everything. So applied to this matrix, because we do not modify the first row and we do not modify the first column. And if we repeat that for this matrix, these are the same number of computations, with the only difference is that the dimension of the matrix now is not going to be m, but will be m-1. And therefore, if we go down back to where our computation count was, or operation count was, we have that, so we discussed the subtractions and the multiplications, and we also see that at every step is exactly the repetition of the previous step, with the only difference that the dimension of the computational problem is diminished by 1. So if the divisions here were m-1, the divisions here will be m-2. If the subtractions here were m-1 squared, they will be here m-2 squared, because the dimension of the problem reduced from m to m-1. And so on. At the very end, we will end up with everywhere ones. And then if we decide to add all of them up, so we will have the sum of 1 to m-1 divisions, which contributes to this sum. And then the number of subtractions is multiplications will be the same. So this is 2. And then we'll have the sum of 1 plus 2 and so on up to m-1 squared. So we have sum k from 1 to m-1 of k squared. We know that there is a formula for the first sum. We know also that there is the formula for the second sum of the squares of integers from 1 to n. It is a known formula. And using this formula, we end up with this particular equation. Now, we discussed that in this case, we are viewing only the terms with the highest degree. So here we'll have the highest degree 2, m times m. Here the highest degree will be m times this m, and the coefficient, so we'll have m to power 3 as the highest degree, and the coefficient will be 1/3 times 1, because the coefficient in front of m here is 1 times 2. So the coefficient will be 2/3 m to power 3. So the operation cost of the Gauss elimination, and actually of finding the matrix U and finding the matrix L, which we get for free because we have computed all these numbers L that the matrix L consists of. The cost of finding the matrix U is 2/3 m to power 3, where the original matrix is a square matrix of dimension n. And now, how do we solve the matrix, the system AX is equal to B? We think of, you can do it the usual way that you know from linear algebra. You have AX is equal to B. Then you do the elementary row operations until you get to UX is equal to C. And then you solve this with a back substitution. To go from here to here, this is this cost 2/3 m to power 3. And then to go from here to solve for x, this is m squared, and therefore the total cost of solving system using Gauss elimination, since here this power is 3 and this power is 2, and we take the biggest power, is 2/3 m to power 3, approximately 2/3 m to power 3. So this can be done. The problem is the following, that sometimes, not the problem, but there is a little caveat And the caveat consists of the following. If, for example, you have a real world problem that had created for you the system AX is equal to B. And somehow the matrix A that is coming from this real world problem is in a way tied to the design of your whatever you would like to design, the design of your object. And B is something that you have to compute that comes to you, for example, from a customer or from some conditions. And every time you end up solving the system, the same system AX, but with different right-hand sides, BI. So I here, maybe I is not B tilde. So one time you have to solve this system AX is equal to B. Then the second time you have to solve this system for another B tilde, AX is equal to B tilde, but the matrix A is the same, just the right-hand signs are different. There are problems in practice that are like that. If you decide every time when the B comes to solve the problem, every time that when you do that, you will have to do 2 over 3 m to the third operations. Then the new B comes, then you have to do 2 over 3 m to power 3 operations, and so on. Every time B arrives, you have to do that many operations, because as we discussed, solving a Gauss elimination, solving the system using Gauss elimination is that costly. Now, what you can do is the following. One can, once and for all, if the matrix A is something that is not changing, once and for all, one can make the computation A is equal to L times U. So one can write the LU factorization of the matrix A. And that way, we will have a cost 2 over 3 times m to the third. And this cost will be done, this computation will be done only once, and this computation, this cost will occur only once. Now, if we have the system AX is equal to B, then this system can be rewritten in the terms L times UX, because A is L times U, is equal to B. And now what we can do is we can set UX to be equal to Y. And if UX is equal to Y, then what we have L of Y is equal to B. So if my B comes, then since I have L in my hand, I can compute this Y easily, because L is a lower triangular matrix, and my cost will be M squared flops. Now, since I will have Y here, by the fact that UX is equal to Y, I know Y, and then I can compute this system to find X using back substitution, because my U is an upper triangular matrix, and the cost will be M squared. And therefore, I will have, every time when a new B comes, I will have just a cost M squared. I will have one time a cost of 2/3 M to the third to do the LU factorization of A. But after I'm done with that, if every time new B comes, I will incur only cost of M squared, rather than every time when a new B comes, I will have this big cost of 2/3 M to power 3. This in some cases actually saves quite a lot, because in practical problems, M can be pretty big. So this is a little discussion about the LU factorization, and why sometimes it is useful to do LU factorization for A and keep it in your memory, and then every time new B comes, just use forward substitution, or back forward elimination, or back substitution. Now, the Gauss elimination is if you think of what we discussed about methods for solving linear systems, we said that there are some methods that are universal that can be applied to every matrix, and there are some methods that are specialized that can be applied for matrices of particular type. So Gauss elimination is a method that can be applied to every matrix, with the little caveat that if our matrix is such that the pivot is non-zero, then we have to do something to the matrix, and we can do Gauss elimination with pivoting, or we can do Gauss elimination with partial pivoting, which we will discuss probably next lecture, but Gauss elimination with pivoting is a universal method. It can be applied for every matrix. Now, this method has a little bit is first of all less costly, and is simpler if the matrix is simpler. And in what sense, if the matrix is simpler? If the matrix, for example, is a tri-diagonal matrix. So before moving to the definition of a tri-diagonal matrix, we'll talk about the definition of a matrix with bandwidth. So a matrix A is said to have a bandwidth 2p plus 1 if the entries of the matrix are 0 outside of the diagonal with bandwidth 2p. And what does that mean? So if I have the matrix A, and if I look, it is a square matrix, and if I look here at the main diagonal, and what I want p elements, because here is A1p plus 1. So from the main diagonal, I want p elements here that may not be 0. Everything else here is 0. And this we do for every element on the main diagonal. So we get up an element of main diagonal, then p elements in this direction and p elements in this direction are non-zero. The rest is all 0. And you can think of it as, that's why it's called bandwidth, because the main diagonal may be non-zero, and then everything basically up and down with the same width may be non-zero, and then the rest is 0. And in the simplest case, when p is equal to 1, what we have when p is equal to 1, the main diagonal may not be 0, the diagonal above the main diagonal, because you have here on the main diagonal, you stay on the same row and go one position to the left and to the right, and one position to the left, and you end up with the main diagonal and the two off main diagonals to the up and down, and this is a tri-diagonal matrix. Even the name tri-diagonal means that 3 strips are possibly non-zero. All the rest is 0. So if one goes a little bit deeper into Gauss, we'll go back to that, but to Gauss elimination and to LU factorization, one can show that LU factorization on a band matrix preserves the bandwidth. And if one does a careful analysis on this, if P is fixed, where P was the bandwidth, remember P was P elements from the main diagonal to the right and P elements to the left. So if this P is fixed and the matrix is of dimension m times m, then the operation count is then m times p squared, big O of m times p squared. So this will be a constant times m times p squared. And you see here that we are saving in terms of operation cost if the matrix is band limited, has a bandwidth. Now, let's go back and discuss Gauss elimination for a particular type of matrix, which is the tri-diagonal matrix. And once again, tri-diagonal matrix is a matrix that has possibly non-zeros on the main diagonal, and it is right here. And so this is the possibly non-zeros on the main diagonal that here has B's, and on the terms above the main diagonal, these are denoted here by Q's, and the term below the main diagonal, which are denoted by A's, and everywhere else is 0. So the LU factorization of such a matrix has a particular name, and it is called Thomas algorithm. And actually, we will talk about it here, and it is much less costly than the LU factorization. So one can check, because of the bandwidth of this matrix, that in fact, if we would like to write down the LU factorization of the matrix A, we know that this is a product of the unit a lower triangular matrix L and the upper triangular matrix U. But as we made the observation below, the LU factorization keeps the bandwidth. So we will have here a matrix U that is upper triangular, but the bandwidth here will be 3. Here we'll have only one element, one diagonal above the main diagonal. And for the matrix L, since it is unit tri-diagonal matrix, it will have ones on the main diagonal and has to have the same bandwidth. So it will have only one term, one diagonal below the main diagonal that probably will be, that may be non-zero. Everything else will be 0. And therefore, if we look at the in the LU factorization will have that property. Now, also note another thing that here needs to be observed is that above the main diagonal we have the, I need to make I want to red here. Above the main diagonal, we have the Q's. So here are the Q's above the main diagonal. And if you do, because we have all ones here, if we do the multiplication, then one can find out that above the main diagonal here in the matrix U, we also have to have the same Q's. Why is that? Because Q here is on position 1 and 2. So in order to, and we know that A1, 2 is equal to our Q1. So I have to multiply, in order to end up with Q1, I have to multiply the first row of this matrix with the second column of the other matrix. Since the first row has all zeros and only 1, 1, so when I multiply by this second column, all the zeros will make the elements below here all 0, and then I will have this term multiplied by 1, and it has to be Q1, so this term has to be Q1. And then again, the same way, one can check that all the elements that are above the main diagonal for the U actually have to be the same as all the elements above the main diagonal for the matrix A, which simplifies the problem even further, that in the sense that the only unknowns then that we need to do to find in the LU factorization are the components L of the lower triangular matrix, which are the elements on the diagonal below the main diagonal, and the components W of the matrix U, which are the elements on the main diagonal. And how we can do that? Well, B1 here is the element that stays on position 1, 1, and therefore it's a product of the first row with the first column, which will give us that W1 is equal to B1. And then what we continue with the next element, second row and first column. Then we multiply, so let's do A2, second row and first column. This multiplies the second row here, which is L21, times the first column here, which will give me L2 times W1. Well, we know W1 from here that it is B1, so this is known. And therefore, the only unknown here will be L2. So L2 is equal to A2 divided by W1. Then we, and in general, one can see that LK is equal to AK over WK minus 1, which we observe here for K is equal to 2. And then we look at the element here at position 2, 2. It is obtained by, so this is the element B2, which is obtained by multiplying the second row of the first matrix times the second row of this matrix. So we have L2Q1, we have L2Q1 plus W2. L2 has already been computed before, so we have L2. We know Q1 from the given matrix A, we know B from the given matrix A, and therefore from here we get that W2 is equal to B2 minus L2 Q1, which is for the general case will give you WK is equal to BK minus LK QK minus 1. So one can simply program that and get then the LU factorization of the matrix A. And if we would like to see the cost of the LU factorization here, we can see at each step how many multiplications and divisions we have. So from K equals to 2 to n, we have one division. So the division is 1 for K from 2 to n. So we have n minus 1 divisions. In this particular case, our matrix is n times n. How many multiplications do we have here? We have one multiplication for every K, and we have one subtraction for every K. So we will have 3 times n minus 1, and therefore we will have a big O of n flops. The operation cost will be big O of n. So to do the LU factorization of tri-diagonal matrix costs us as little as a big O of n, where n is the dimension of the matrix. And now, once we have this LU factorization, as we discussed before, we solve the system AX is equal to B by writing, instead of the matrix A, we write L times U, and then we think of UX as a vector Y, and therefore first we have to solve the system Ly is equal to B, and using the forward elimination. And how do we do that? Looking at how the system how the matrix L looks like, it's even simpler than a regular lower triangular matrix, because it has only one element. That is, for every row, there are only 2 unknown elements. And if we start with the first one, L1, Y1 is equal to B1, and then we look at the kth equation, this will be the kth equation, and we can express by that time we will have had computed YK minus 1. We move it on the other side, and therefore this will be the formula for YK. And we see here that for K from 2 to n minus 1, we have for every K from 2 to n minus 1, we have one multiplication and one subtraction. So we'll have of order n, the number of division, the floating point operations. And then if we look at the backward elimination, because of the form of the matrix U, we see that on each row we have 2 unknowns, And again, we write the backward elimination, taking into account what is the particular form of the matrix U. So the last equation will be this, and we'll have one division. And then the next equation will be this one. By the time we arrive here, we will have had computed. So here is U. Let me see. I have Y, and then we have UX. So here is XN here, because here is XN and here is XN. So here is a misprint. These are all X's. And here is X. And here is X. And here is X, because we need to compute X. We don't have U. So we have WN XN is equal to YN, from where we get the XN. And then we have at every row WK WKXK plus WKXK plus 1, because it is upper triangular matrix, will give us YK, and therefore we can express the XK in terms of the other ones that we know. And here we see that at first step we have one division, and then for every subsequent step, every time we'll have a division. So as a total, we will have n divisions, and then we'll have if the order n multiplications and subtractions. So the total number of computations of floating point operations then will be a big O of n. Which means that if you have a tri-diagonal matrix and you would like to solve the system AX is equal to B, and the dimension of the matrix is A, then it is much cheaper. The Gauss elimination is much cheaper in this case, since the number of computations is a big O of n, while the cost of operations is big O of n, while if you have the general case, it is 2/3, 2 times n to a power of 3. Then the natural question is, we have discussed this, the Gauss elimination and the LU factorization for a matrix A in the case when the pivot elements A, K, K, K are all different from 0. So after you perform a step in Gauss elimination, you end up with a pivot element. If this element is different from 0, then you can go ahead and perform one more step. And then the Gauss elimination will be possible. Now, if we have a case here, for example, the matrix A is the simple matrix 0, 1, 1, 1, where the first pivot element here is 0. And the question is, does this matrix have a LU factorization? So let's assume that it does. If it does, then it will be representable in this form, where the L is a lower triangular matrix with ones on the main diagonal, and we have the upper triangular matrix U. And since this term here is 0, so we'll have which stays in position 1, 1, then we will have that the product of this row with this column should be equal to 0, which will give you that U1, 1 should be equal to 0. And also at the same time, we have that if we look at this element here, which stays on position 2, 1, then this element is the product of the second row times the first column. So we will have that 1 will be equal to L21 times U11 plus 0. And therefore, we have this equation for the U11 and L21. And this cannot be, because then we cannot have 0 times something to be equal to 1. This tells us that if we have that some of the pivot elements are equal to 0, we can not do an LU factorization, and in the usual way that we discussed, we cannot do Gauss elimination because we have our pivot element that is 0 here, and we cannot divide by it. So what do we do in this case? Before doing that, I want to discuss also a slightly different issue. So let's say here we didn't have a 0, but we had a very small number, 10 to power negative 20, which is a perturbation of the case that we had. And then one can actually do Gauss eliminate, LU factorization. One can show that the matrix A is equal to the product of the matrices L and U, and one can see that this row multiplied by this column will give you 10 to the negative 20. This row multiplied by this column will give you 1, because 0 will make this term 0. Then 1, this multiplied by this 10 to power 20 times 10 to power minus 20 will give you 1. And then this term multiplied by this term, this row multiplied by this column will give you 10 to power 20. And then it will give you plus 1 minus 10 to power 20. And as a result, you will end up with the 1 right here. So this matrix, which can be viewed as a perturbation of the original matrix, actually does have an LU factorization. And let's say we would like to solve the system AX is equal to B, where the right-hand side is the vector 1, 0. And one can check, since this is a 2 by 2 case, that the solution is closely is like minus 1, 1. Now we are doing everything, even though it is a 2 by 2 matrix, it is very illustrative as to what happens when we do computation with a computer. In double precision, the machine accuracy is 10 to, the machine epsilon is 10 to the negative 16. And we know that the computer rounds to the nearest floating point number, and let's us assume that because of this rounding, the computer keeps 10 to 20 will be a very big number, so the computer is not going to see 1, and the computer will keep, instead of 1 minus 10 to power 20, which is this number here, the computer will just keep 1, keep minus 10 to power 20. So this will be what the computer will keep. It will keep the same L, but will keep an approximation to U, which is the approximation that it drops the 1 here, because 10 to power 20 is very big, or minus 10 to power 20 is a very big number in absolute value. And thus, when we look at the matrix L tilde multiplied by the matrix U tilde, we will end up with a new matrix. And this matrix is the matrix where will be the same as the original matrix, with the only difference that this term here in the original matrix was 1. And this term here in the resulting matrix is going to be 0. And therefore, when the computer does the LU factorization, actually it's not going to solve the original matrix, the original system, but will solve a system with this matrix. And therefore, it will give a solution that is this solution. So the original solution was close to minus 1, 1. And what the computer computed is the solution 0, 1. So what is happening is that even though the computer saved an approximation to L, which basically here is the same L, and the computer saved or worked with an approximation to U tilde, and they are U tilde is close to U and L tilde is in fact the same as L. When we wanted to compute the system AX is equal to B with the matrices L tilde and U tilde, we ended up with a big difference. We ended up with a vector that is very different from the vector that was supposed to be the solution of our system. So one has to be careful about this. And this is related to your last homework problem, in which you are asked to recover certain coefficients of a certain polynomial, which we know what they are all ones. But if we try to find them and write down the system for them, then the matrix of this system is ill-conditioned. And if you reach to a matrix of a particular size, then after that your Gauss elimination is not going to give you results that are actually a good result. It's gonna the round of error is going to accumulate, and it's you are not going to be able to perform any sensible computation, even though on a piece of paper everything should be okay, and on a piece of paper the Gauss elimination should work. So in order to overcome these problems or problems of this type, however, there is a bigger discussion about stability of Gauss elimination, which I'm not going to go into since this is not a numerical linear algebra class. Some of those problems can be softened if one uses the so-called pivoting strategies. So before going further, I am just going to mention a theorem which we are not going to prove. And the theorem states the following, that if we have a matrix of dimension m times m, such that all the matrices that are derived by its upper right, upper left corner. So here we have A1, 1. This is one can be viewed as one matrix. Then we have this matrix A2, this upper left corner matrix, and so on. The upper corner matrix is A11, A1K, AK1, AKK, where they are denoted by delta K. And let's the A be such that all these matrices for K from 1 to M. So we start cutting off this upper part of the matrix consecutively until we end up with K is equal to M, which basically encompasses the whole matrix. If the matrix A satisfies this condition, then the matrix A has an LU factorization. So A can be written as L times U, and the matrices L and U that participate in this LU factorization are actually unique. As I said, we're not going to go into the discussion of that, but this is just a theorem that tells you that there are cases in which, based on the properties of the matrix A, you can guarantee that the matrix A has an LU factorization. So I will stop right now because I went over time. What we will do next time we will talk about pivoting and partial pivoting, and why we need to do that, and even sometimes when it is not necessary to do it, we do something called partial pivoting, in which we are trying to diminish the propagation of round-off errors. Okay, so the homework is based only on the material up to now. Next week, we will continue with Gauss elimination. After Gauss elimination, the discussion will be we will talk about iterative methods for solving linear systems. And then we will continue with numerical integration, numerical differentiation. Is not going to be in this order, but solving nonlinear equations and other discussions. Okay, bye.